So it's 1.3 stoichiometry. So the following equations represent the reaction when solutions of sodium carbonate and calcium chloride are combined, and it gives you the full molecular equation, balanced, and it gives you the net ionic equation. For keeping this short, I'm going to just write the net ionic equation. This is what actually happened, and ignoring the things that were aqueous at the beginning and the end. Whenever you write stuff like this, be in the habit of writing the states. On the AP exam, if they have you write an equation, it needs to have states. So a chemical reaction happened. Number one, what evidence would you expect that shows chemical reaction occurred? What happened here? So let me describe to you maybe a little bit more what's going on. We have two solutions, calcium chloride and sodium carbonate, and we are pouring them into the same container, and then we end up with an aqueous solution and a solid. And so it's really this that shows us a chemical reaction happened. A precipitate formed. The term precipitate means a solid that formed from two solutions. Number two is talking about conducting electricity again. What determines how well a solution conducts electricity? And just a quick answer, it's the amount of dissolved ions. So for instance, our tap water here is better than it used to be. It's still pretty hard. It's got a lot of calcium in it. Calcium ions conduct electricity. So if you ran electrical current through our tap water, it would conduct. If you got a bucket full of seawater and tried the same thing, it probably has 10 or 100 or 1,000 times as many ions. It would conduct electricity a lot better. So it's just the amount of the ions. Okay, so now we are looking at number three, the actual stoichiometry stuff. Suppose a solution contains 4 millimoles calcium ions, represented in the first row of the table below. Quantities of CO3 are added 2 millimoles at a time to the solution in separate steps. So for each step, number one, complete the mole chart to show the amount of each ion present in solution. Number two, sketch the particulate diagram that represents the solution. Don't include the solvent, so no water molecules. Number three, identify the amount of precipitate formed and the limiting and excess reactants. Predict with relative numerical values the conductivity. Okay, so here's what we are looking at. So I'm going to reproduce the table that you're looking at. Step A, 0 millimoles. A sketch of this solution. What does it look like? So remember what we started with. It was calcium ions. We've not added anything. Nothing has reacted. So all we have are calcium ions. So we are starting with 4 millimoles. So it makes sense to me in the picture to have 4 calciums here. This one's already drawn for you? Okay. Are the other ones?
No.
Okay. So then there's a mole chart, which it looks like they are drawn for you, but not filled in except the top one. So the mole chart for this, so basically what you have is initial, change, and final. You have calcium plus carbonate yielding calcium carbonate. So we're looking at initial concentrations. Initially, calcium is 4. This one is 0. There's none of it. And there is no calcium carbonate. We didn't add anything, so there's no change. And so the final looks just like the initial. So that's what it's going to start with. So let's give it a conductivity number just to estimate. Let's say it's 400. Is that already written too? Okay, for step B, we have added 2 millimoles of this carbonate ion. So what's going to happen? Well, let's do the chart first, and maybe it will help us out a little bit. Initial, change, final. Here are the initial amounts. We had 4 millimoles of calcium, 2 millimoles of carbonate, and 0 of the product. Now is your stoichiometry. This is the point where you could do all that dimensional analysis, but look at this, all the coefficients are 1. So that's going to make this one a little easier, because we're not worried about coefficients right now. Remember the mole ratios? Every mole ratio here is 1 to 1. So we're going to use up as much of the products as we can, which is this one. We're going to use up all of the carbonate, and that's going to use up 2 of the calciums. And when we lose 2 of each of these, it's going to add 2 of the product. And then our final, calcium is 4 minus 2, 2. Carbonate, 2 minus 2, 0. Calcium carbonate, 0 plus 2, that's 2. So then it says estimate the conductivity. Remember, it was somewhat dependent on the concentration of ions. So it was 400, now the concentration is half. So we'll say the we'll say the conductivity is also half of the original. Now it's 200. It's your desk wet again. Okay, so let's go back and draw this picture now. So we're going to use the final. So at the end of this step, we have 2 calciums left over. So here's a calcium, here's a calcium, and on the bottom we have our solid product. It's not labeled, but this is the solid calcium carbonate. Just a white precipitate on the bottom. See if I can confuse at the moment. Step C. Four millimoles. So in this reaction, what's happening is we're taking some of the original solution and now we're adding 4 millimoles of carbonate. So we're basically going from A to C and we're acting like this experiment is over. B is done for. Now we're just going to start over. So beginning with our chart, we have 4 calciums and we have 0 solid calcium carbonates. It says we are adding 4 millimoles of this carbonate ion. So your chart in the initial reads 4, 4, and 0. So the one with the least number is what we subtract by, but they are the same. So it's going to be -4 and -4 for both of them. We're doing +4 for the product. So what's going on in the final? 4 minus 4 is 0 calcium, 0 carbonate, and 4 calcium carbonates. Okay, so the conductivity of this solution, 0. There's no dissolved ions. Something that I neglected to write down, but it looks like you've already done it. In step B, the limiting reactant was carbonate. Because it ran out first, it's got a 0 down here. And the excess reactant was calcium. We have some left over. Here, it's neither one. Neither one limits, neither one is excess. This reaction worked out perfectly. So the picture, all you're going to have is a big pile of calcium carbonate on the bottom. No ions. That's going to be it. Step D, so we're starting the reaction over completely. We're adding 6 millimoles of our carbonate ion this time. Beginning with the chart, starting with 4 millimoles of calcium, 6 millimoles carbonate, 0 the product. The change is going to be minus the smaller one, so we're going to use up all the calcium. It means we can only use 4 of the carbonates, which means we can only make 4 calcium carbonates. No calcium left over, 2 carbonates left, and we produced 4 calcium carbonates. Conductivity of the solution. Well, last time that we had 2 ions left over in the solution, the conductivity was 200. This time we have 2 ions left over. It's 200. Limiting reactant. Limiting reactant is the one that ends up with 0 in the final. Calcium. Excess, we have carbonate left over. And then a picture. We have a lot of calcium carbonate on the bottom. have 2 millimoles of carbonate left over. Looks like a face. Looks like everybody's catching on and working pretty quickly. So we've got one more to do here. Original calcium 4, adding 8 carbonate, using 4 calciums, using 4 carbonates, making 4 of the product, 0, 4, 4. Conductivity, you could probably guess, is going to be 400. Limiting, calcium is at 0 at the end. Excess, we have carbonate left over. And then we can just draw a picture. Okay, so on the next page, number 4 says sketch the following graphs. Okay, so it's drawn the grids. They're labeled too. Not labeled. Okay. So we have one right here. Okay, so sketch the following graphs. The first one is the amount of calcium carbonate formed versus the amount of carbonate added. Amount added vertical is product formed. Okay, so in the first scenario, we added, and I'm going to say these go by 2s, really. Yeah, everything went by 2s. So when we added 2 millimoles of carbonate ions, we ended up with 2 millimoles of this calcium carbonate product. When we added 4 millimoles, we ended up with 4 millimoles of the product. So far, we have this linear graph. It was also at 0, 0. Up to this point, here's what it looks like. Every time we add reactant, we get product. But there's a point where we ran out of calcium. And we ran out of calcium because we only had 4. So even though we added 6 carbonates in the next trial, we only had enough calcium to make 4 calcium carbonates. And so the graph takes a turn to the horizontal. And then in the next trial, we had 8. Same thing. We were only able to make 4 of the product because we ran out of calcium. Second graph is relative conductivity. versus the amount of carbonate added. So graph's going to look something like this. So when we added 0 carbonate, the conductivity was here. When we added 2 of them, there were half as many calcium ions left. It was here. When we added 4 millimoles of carbonate, everything was gone except the solid product, no conductivity. And then it starts to go back up and looks something like this. Going down, hit 0, going back up, going back up. And this is really proportional with our excess reactants. So explain the shape of the graphs. For this one, the amount of calcium 2+ is fixed. So calcium carbonate is formed only until calcium is used up. And we can see on this graph the point where the calcium runs out, and that would be right here, because then it just levels off no matter how much carbonate we add. This one you can write down something. I think you already get the idea, so I'm going to move on. Conductivity depends on how much ions are there. Okay. Number 5, it says, suppose in the experiment we did not know how much calcium ion was present to start with. Propose an experiment to determine the amount of calcium. So, we look back at the graphs. We know how much carbonate we're going to add. Any given time we can measure it and we add it, and we can use this to figure it out. So one way to measure it, you could do it over here and just wait for a solid product to form, but that's probably less reliable than putting some electrical probes in it and measuring the conductivity. So there's some amount of calcium, and so you could just put the electrodes in and measure the conductivity and add a little bit of carbonate at a time. Wait till it hits 0. Then you'll know how much carbonate you added. So you'll know through stoichiometry how much calcium was there. Maybe you describe this in your own words. Okay, there is a second possibility. You just add a bunch of carbonate so that a precipitate forms, and then just keep adding carbonate until you're sure that there's no more solid. Then you filter it out, rinse it, let it dry, measure the mass. That's the second possibility. Maybe we should try that one as an experiment, so you can get the filtration techniques. Write that down.
Are those supposed to be just for experiment like this?
No, I use Post notes for everything. There's not very many today, but I usually have a to-do list on my desk. When I worked in a hospital, I had like a row of Post notes for different topics. That's how I organize things. So I think at the bottom it describes to you titration and gravimetric. So I would say just take a look at those later. I'm not going to read them out loud to you. There's really nothing that happens. So let's do a couple of practice problems. There are 3, 6A and B, 7A and B, and number 8. So let's look at, let's just start with number 6. So here we have the same reaction that we've been talking about for the whole day. Sodium carbonate plus calcium chloride yields calcium carbonate, which is a solid, and then you end up with 2 sodium chlorides, which are still aqueous. You've got this part typed in. A 100 milliliter calcium chloride solution is titrated to the equivalence point. Let me go back and talk about what this means. Titrated means we're adding the second substance, and this is basically the equivalence point. We want it to be where it hits 0 across this table. So basically, we want to get it to where we have this one. That's our goal here. So let me start writing things down. 100.0 milliliters calcium chloride to the equivalence point with 50.0 milliliters, 0.20 molar sodium carbonate. Okay, so all of this is written on the question. What is the concentration of the calcium chloride solution? So usually the way I teach this in Chem 1 is to do all the steps in one big thing. But let's go individually through the steps, and then I'll show you what it looks like in the long version like I would probably do. First thing we probably want to know is how many moles of carbonate are we adding? Remember, everything needs to go back to moles. How much carbonate are we really adding here? So here's what we're going to do. Here's the volume, and multiply that by the concentration, which is moles per liter, or you could say moles per 1,000 milliliters. So you could save yourself some time and just skip a step there. The milliliters would cancel. This is actually a formula, a generic formula on your formula sheet. used to be. Basically, moles is concentration times volume. So concentration times volume. 50 times 0.2. So there's 10 divided by 1,000. Somebody check me on the calculator. Just grab one to divide by. Okay, one more zero. Good. Thank you. And it's moles of carbonate ions. So if we want to know the concentration of the calcium chloride solution, we need to know how much calcium is going to react here. Moles of calcium ion. This is your stoichiometry step. I think I have one too many zeros. Starting with our moles of carbonate. And then the mole ratio that compares carbonate to calcium. And you look up here, here's your calcium, here's your carbonate, it's 1-to-1, and this number is the same. The last piece of information that makes this one concentration is going to be what is the volume of the solution now. So here's what we're looking for. Brackets, Ca2 plus, close the brackets. The brackets mean concentration. This reads concentration of calcium ions. And so we need moles per volume. So we have moles of calcium ions divided by what's our solution going to be. So we're looking at the original solution of calcium. We want to know how much the concentration was originally. And it had 0.1000 liters. So 0.01 divided by 0.1. I don't trust myself. .1. I would label this with a capital M, molar. It just means moles per liter. And that's calcium ions. If you wanted to, you could label it as 0.10 moles per liter. That's just more writing, it's more typing.